Okay, so this is this is our project, Smart Parking using Virtual Memory. Our team name is Team TechSync. My name is Vidya. I'll be presenting the first part. So, that's it. So the memory management is essential in operating system, especially when it comes to physical memory. When the physical memory is very limited, so Beijing solved this problem by dividing the memory into equal size blocks by storing them in available forms. However, understanding this process can be difficult. So our project introduces smart parking system as a simple analogy, which means the cars equals to memory pages and the parking slots equals to the memory frames. So when when a lot of it is full. Anyway, so the FIFA policy decides which car is removed, just like the page replacement algorithm. And this simulation helps us see the concepts like addressing mapping and page faults and making complex memory management ideas more understandable. So in the intro, as the application grows, the memory needs to increase beyond the physical availability. Operating systems use virtual memory and paging to manage this. Paging allows non-continuous memory allocation, handles overflow using page replacement strategies, but some concepts are harder to grasp due to the abstract nature. That's why we built the smart parking system using paging, where a real life scenario mirrors how paging works by linking cars to the memory pages and the parking lot stalls to the memory frames. So we make a technical OS topic easier to learn and visualize. Also, this is a problem statement. Students often struggle to understand how memory is managed in real life systems. So how we address this translation works, what causes page fault, and why we need the replacement policies. So to solve this, we use the real. Oh, one sec. To solve this, we use the real life. Wait, one sec. To solve this, we use real-life models of cars. As I stated before, the cars present the pages. When too many cars arrive or like too many pages are there, the memory is full. So the FIFO decides to leave, but this stimulates the memory to overflow and replacement without proper memory handling. The system will slow down drastically, similar to cars entering and exiting a lot constantly without parking. This is known as thrashing in memory systems. Our goal is to visualize paging and explain and address the translation and faults early and demonstrate why it's effective to use memory use in performance. Okay. I pass it to the next person.
So next, I'll talk about the related works. As paging is a crucial concept in operating systems used to manage memory efficiently by dividing it into fixed-size pages. However, due to its abstract nature, many students struggle to understand how it actually works. To address this, previous educational tools and stimulators have tried to visualize paging, but most remain too technical or disconnected from real-life experiences. While analogies like warehouse storage or classroom seating help, they still lack strong engagement. Our project introduces a smart parking system as a novel analogy. In our system, cars represent virtual memory pages and parking slots represent physical memory frames. When the lot is full, we use the first in first out FIFO method to remove the oldest car, just like how pages are replaced in memory. This analogy makes complex concepts like page faults and replacement policies easier to visualize and understand. Following up, I will talk about the methodology. Our project followed a structured 5-phase methodology. At first is the planning phase, in which we formed our group, selected the topic, and chose the parking lot analogy to represent paging. Tasks were also divided among members. Then, following up is the requirement analysis phase, in which we researched virtual memory, page tables, and FIFO algorithms. We decided to implement the simulation in C++ using a simple console-based program for portability. Following up is the review phase, in which we submitted our proposal for lecturer feedback and improved it based on suggestions, ensuring our simulation met both educational and technical goals. Following up is the development and testing phase, in which we built the system in C++, allowing users to add cars which act as pages, simulate time to decrease the page duration, view current slot and queue status, and automatically replace cars using FIFO. We tested it with different scenarios to verify the correct behavior. Lastly is the finalization phase, in which we documented the results, created this presentation video, and compiled our final report. The project demonstrates how a simple analogy can help learners visualize paging more efficiently. And that is all for my part. I will now pass to the next presenter.
So I'm presenting about the design implementation. So first is the system design overview. The simulation models virtual memory paging using a smart parking system analogy. So the concept is that a virtual page represents the incoming vehicle. Physical frame represents parking slot. Page 4 is no free slot available. Page replacement using first come first served concept is the oldest car is removed. So the system is menu driven and runs in a loop, allowing users to first add new vehicles, which representing virtual pages as stated before. So also simulate time passing to handle state duration manually by tester for better testing and learning. Also, it can view the status of the parking slot like memory storage and automatically replace a vehicle using first come first serve. And then it will automatically replace a vehicle using first come first serve when memory is full. And then will be the component of design. Okay, so here a car, which is also the page here object, represent a unit of data to be stored in memory. The attribute we use is ID, state duration, in unit, and arrival time or entry order for first come first tracking also. So the slot or frame object represents a physical space in memory. The attributes we use is slot ID, occupancy flag, and car object if occupied. Then will be parking system, which is the memory manager. It's responsible for allocating cars to available slots, managing the waiting queue, handling page faults and replacements, and simulating time progressions. And the implementation is C++ console application. The data structures, which is simple counters for tracking car IDs and simulation time. So here are the libraries that use. And then the core functionalities, first is the car arrival. Sorry, can scroll up. Okay, so first is the car arrival. It creates a new car with specified stay duration and checks for free slots if available, parks the car. And if not, it will add the car to the queue. And then next to it is the code that we use. Let's scroll down a little bit. Okay, next is the time progression, which is the decrements, the duration of each parked car and call the function once will decrease one time unit, which means that one time unit is passed. If a car's time is up, removes it and frees the slot. So if the queue is not empty, you assign the next car using first come first served concept to the free slot. And then FCFS placement logic. When a parking slot becomes available, the car that has been waiting the longest is assigned to it. And then next is the logic for what we want. Next is the display status. It prints current state of each slot using the car ID and duration left. And it also shows current state of waiting queue. The next is also the logic for printing the status. Last is the menu system. A while loop with user input to add cars, simulate time, display current status, and exit the program is used so that user can choose what they want to test in this program. So I'll pass the continue to Jiang.
Okay, I will introduce the results and the discussion. The smart parking system implemented as a C++ application effectively simulated virtual memory parking using a FIFO page replacement policy with three parking slots representing physical memory frames and vehicles as virtual memory pages. The system was tested with scenarios involving five vehicles with varying state durations. It successfully demonstrated page allocation and FIFO represent, such as when a vehicle enters a queue due to full slots and parks when the slots freeze up. Uh, Manual rule parking behavior. The simulation clarify abstract concepts like tables and address mapping through a real-time melody. However, testing revealed the limitations of FIFO, such as sub optimal replacement, highlighting potential inefficiencies compared to organisms like LRU, thus reinforcing the system's educational value in visualizing memory management. Okay, next part is the future and conclusion. Okay, future future enhancements for the smart parking system include uh, incorporating additional page replacement organisms such as LRU to compare their efficiency. Developing a graphical interface using SFML could improve the user engagement. Additionally, introducing complex uh, scenarios such as uh, variable slot size could be beneficial. In conclusion, the system successfully simplified virtual memory packaging the mapping page to VS Code and frame to slots, making concepts like FIFO replacement more accessible. Positive testing feedback confirms its effectiveness as an educational tool, with potential for development to enhance its impact for operating system learners. I think that's all from our group project presentation. And thank you for listening.
So now we'll do the system demo. So at the initial state, all slots are empty and the available slots are slot 1, 2, and 3. So now it's time 1 and vehicle 1 arrives. So let's select a car arrives. And then you ask for the state duration for the car. So from the test case, we can see that the duration is set as 6. So here you can see that it's parked in slot. And then let's proceed with time 2. So this we need to manually passing the time. And select 2 is passing 1 time unit. So now it's time 2. Also the same vehicle to arrive. So select car arrives. And then the staying duration for vehicle 2 is 4. Also the same car 2 is parked in slot. So passing 1 time unit again. Now it's time 3. Vehicle 3 arrives. And then the stay duration for vehicle 3 is 5. So the same is parked in the slot. So now going to time 4. Vehicle 4 arrives. Now the car arrives, and then the duration for vehicle 4 is 3. So it says here, no slot available. So car 4 is added to waiting queue. Let's go to time 5. Maximum time. And then at time 5, car 5 arrives. The duration for car 5 is 1. Also the same, it says that no slot available and is added to the waiting queue. So now the waiting queue has vehicle 4 and 5. The remaining duration for the cars in the parking slots are V1 that has 2 time unit, V2 that has 1 time unit, and V3 that has 3 time unit. So let's check. Yeah, so you can see that all are correct. So going to time 6. Now it says that car 2 left the slot, and then car 4 is parked from the queue. And then let's check the status again. Yeah, so now the slots are occupied by car 1, 4, and 3 respectively, while car 5 is still in the waiting queue. Even though car 5 has shorter stay duration compared with car 4, but since we are using the first come first served concept, so the car 4 is prioritized. So let's proceed with time 7. On time 7, V1 duration reaches 0, so it's left a slot, and then V5 from the queue parks in slot 1. And now the slots are occupied by V5, 4, and 3 respectively, which is the status. And So yeah, so it's correct. And then the waiting queue becomes empty. So after this, there will be new cars coming in, and then the cars parking here will leave. So apply the same logic as the test case above. So there will be all for demo. Thank you.